Lab 2 for Physics 2, the revisit to the Charged Tape Lab. A quick introduction: there was no real experiment for this lab, and instead we actually utilized our data from the first lab and expanded upon those calculations, showing the tape as a whole object instead of as a single point, as well as including the electric field vectors along every point of said tape. The code involves creating a computational model with two lines of tape particles parallel to each other and how the electric field at each dq of the top tape counteracts the forces of gravity. The purpose was to further elaborate on the effects of electric forces between legitimate objects as opposed to idealistic point charges, and to find the magnitude of the charge on one piece of tape. So here is a quick preview of the results. This represents the top floating piece of tape. These represent the actual electric fields along each point. This is the net electric field and the gravitational force. And this is the lower piece of tape right here. And as we can see, the magnitude of the electric and gravitational force are equivalent. So some of the principles that were utilized are Coulomb's law, which states that electric force between two charged particles is directly proportional to the charge of the objects and inversely proportional to their distance. This explains why the distance between the two charged pieces of tape has to be so small, seeing as the charge on both is very small. Newton's second law is also being utilized, as this allows us to find what the force of gravity is equal to, and thus also tell what the electrostatic forces have to be equal and opposite to in order to keep the tape floating. So here are the equations that we actually used. The equation for Newton's second law, with the force of gravity being equal to mass times the acceleration due to gravity. There's the Coulomb's law equation, which states that Q is equal to K times Q squared over R squared, where Q is the charge, R is the distance between the two objects, and K is the Coulomb constant. And then here we have the difference in charge over a small section of length, and then here we have the different amounts of charge and energy. And the system actually includes the top piece of tape floating, and the surroundings involves everything else in the universe, including the lower tape. Some assumptions that were made are setting up the tape as a non-moving object with acceleration equal to 0. Resistance and other forces are being ignored, and the charge is static and evenly distributed across the tape, and the electric field from the top tape itself is ignored. The code for Lab 1 effectively was the experiment. It said Lab 1 code was produced through this experiment, charging a U-tape by ripping that tape on top of another tape, holding one tape up above the surface, and then holding another one to make that top one float. And then the code for this lab then established a very simple model of the electric field and force of gravity, leaving both pieces of tape as a point charge and the electrostatic force being one large force instead of the accumulation of multiple small ones, in addition to finding the charge and number of electrons on each piece of tape. Here was the results from Lab 1, and effectively the experiment picture with this blue orb representing the top piece as just a point charge, same with the bottom piece of tape being this red orb. This green arrow was a force of gravity, and this orange one was the electrostatic force. Here we have the initial condition set up, with this being equal to K UPES, acceleration due to gravity, the mass of one piece of tape, and then the initial estimate of the net charge on one piece of tape, as shown here. Here is the actual calculating code. It's a little bit hard to see, but this line right here represents the actual, floating top piece of tape. This one represents the bottom piece of tape. Here we have the scales to make sure that they all show up correctly. Here we have the individual electric fields along each point of the top tape. Here we have the accumulated electric force vector established on this line, and then we have the gravitational force counteracting it. And then here we have the code output. It's fairly similar to that of Lab 1, but a little bit more detailed. The red orbs this time actually represent the top piece of tape, and the blue ones represent the lower, with these representing the minute and relatively insignificant electric fields along each point of tape, but they all accumulated to be this equal to this white arrow, which is counteracted by this yellow arrow, which is equal to the force of gravity, and these are also equal and opposite as shown here. The way in which the computational model shown from the previous slide and the experimental data are similar is that they both literally showcase how the top tape floats due to equal and opposite charges. Not only that, but both rely on Coulomb's law in order to demonstrate why this floating occurs. The computational model is different from our experimental data in that the model is using a line charge approximation as opposed to a point charge. This difference in approximation also leads to a different magnitude of the charge on one tape, with the new model having the charge on the tape being approximately 6.18 times 10 to the negative 7 coulombs based on the charge found in the experimental data multiplied by the square root of the gravitational force over the magnitude of the initial net electric force. Some potential sources of error include a non-uniform charge distribution, air resistance, over-approximating things like the length of the tape, coming into contact with the charged tape with our fingers and such, and the assumed density to calculate the mass of the tape. Now, what if you had modeled each of your tapes as a single point charge like in the previous lab? Compare the estimated value of the charge you get when you In the line charge model, we found that the charge of equilibrium is approximately equal to 6.18 times 10 to the negative 7, and using a point charge approximation, the Q shown would be roughly an order of magnitude smaller because the point charge model overestimates the electric field at each charge by concentrating all the charge at a single point. Why do these estimates differ? Which value is more likely to be closer to a real value and why? As stated in the previous question, the reason these estimates differ is because the point charge model overestimates the electric field at each charge and ignores the spatial distribution of charge along the tape, kind of like using too large of an interval as part of a Riemann sum to properly estimate the area under a curve. And then the line charge is more likely to be closer to the real value because it better represents the actual distribution of charge across the tape.